So, hello everybody. I'm sorry you can't see me. For some reason, Zoom doesn't think I have a webcam, even though I do. I mean, it was on for a few seconds when we started, but it's disappeared. Anyway, the idea of the talk is to talk about a little adventure I've had with machine learning. Don't read too much into it, but I think there are some things which people may find of interest. So the context was that back in January, there was a challenge posted on the decision management community website about NIM rules. And the idea was basically to determine the rules for playing a particularly simple variant of the NIM game. And the game really is very simple. It's as follows. You have a number of balls or some other kind of object. I mean, it's often played as a kind of pick up sticks sort of game. The challenge specified 15 to 17 balls, so most of the scenarios will be around that. And the idea is you've got two players who alternatively remove balls from the original pile. The player must take at least one ball, but they can take up to three. And the person who takes the last ball loses. And just to give a quick flavour of it, suppose we have Alice and Bob playing and they start off with 7 balls. Alice goes first because she's a girl. She takes 3 balls, Bob takes 2, there are 5 left. Bob now takes 3 balls, there are only 2 left. Alice is sensible enough to say, I won't take both of them, I'll just take one. Bob is left with the last ball and loses. Alice wins. Now, when we actually sort of go back to the challenge and think about what's involved, what we want to do is we want to build an algorithm or a program of some sort which is going to play NIM well in some sort of manner. So basically what we have to do is create an algorithm which will figure out what is the right move to make when it's the algorithm's turn. Now, there are a number of options that we have. I mean, the simplest option is we just get the algorithm to make a legal move. Pick one at random, but obviously that's not going to play the game very well. The second option would be perhaps to sit down and work out an unbeatable strategy and then implement it. And in practice, that really shouldn't take you more than about 10 or 15 minutes because the game's nice and simple, and it probably doesn't take you more than about 10 or 15 minutes to implement. But what I thought, and something that Jacob hinted at when he produced a solution to the problem, was that a third option, which would be much more interesting, would be to try and build a program which learns how to play well all by itself. And that's essentially what the story I'm telling today. So we're talking machine learnings. What are the options? I have a book on machine learning. Unfortunately, I haven't actually read it, but I sort of had a look at the chapter headings, and these are the sorts of methods that were available to me. And it went on and on. And at the end, I was thinking, well, I don't know how to apply any of these or which ones are actually relevant to the sort of problem that we're looking at. So my thought at this point was, and I said, well, why don't we work from first principles instead? So the inspiration was, I have heard this remark bandied around that AlphaGo learned how to play Go by playing itself. So it figured, what on earth does that mean? But I figured I could do something along those sorts of lines. So the idea I had was to build a framework where I had players playing one another using a strategy, and the strategy is just how you determine how many balls to take at each stage, and then record which moves resulted in wins and which moves resulted in losses, and use that as essentially a mechanism of amending the strategy so that in the future I would make moves which resulted in a win in the last game I played more likely in the future, and moves which resulted in a loss in the last game less likely in the future. And hopefully playing again and again, amending the strategy each time round, then the computer would learn to a good strategy, one which would be successful. So first steps, choose an implementation technology, and I decided to use Python, partly because Python was in my head because it seems to be the language of choice for doing machine learning, and partly because I'm trying to learn how to program in Python anyway, so it's good practice. I built some basic playing logic so I could get 2 players to play one another using a strategy that they were learning. And the key thing was really at the end of each game to make a list of the moves that were made during the game and then feed that into the machine learning algorithm. Now, why do we do that? Well, what can you get from the moves of the game? Well, the game is just a simple Python list. So, for example, here we have a game where Alice took 3 balls to start with, Bob took 2 balls, Alice took 1 ball, Bob took 3 balls, and so on and so forth. And what can we get from that? Well, I mean, how many balls were there to start? We can just add up all the entries in the list. More interestingly, if we see whether there were an even number of moves or an odd number of moves, we can tell who won. So if there were an even number of moves, it was the first player who won. And if there were an odd number of moves, it's the second player. And that's simply because if it's an even number, then it must have been the second player who took the last ball. If it's an odd number, it must have been the first player. The other thing that's interesting is that we can see that we have multiple games here. It's not just one game starting with 17 balls, but we've actually got another game where if we forget about the first move, that's a game which started with 14 balls, and instead of the first player winning, it was the second player who won. And if we knock off 2, then we can see this is a game, this list describes a game starting with 12 balls where the first player won. The next question was, okay, well, I have this data, but what am I supposed to be learning from this? I mean, after each game we learn something, but what do we learn? Do we keep all of this information, or do we throw some of it away and be a bit more selective? And I wanted to try and retain a fairly high level of information, because it didn't seem to me that it would be particularly sensible for us to try and remember every game that we played. So what are we getting out of it that's useful? Well, what seemed to me and went back to the kind of original thoughts was that we know when we have a particular number of balls to start with, and we make a particular selection to say either we take 1, 2, or 3, we know at the end whether we've won or not. So, for example, taking the previous example, when we had 14 balls left and 2 were taken, the game was lost. When we had 12 balls left and 1 was taken, the game was won. So why not keep for each starting number of balls that we have, and for each number of balls we took in that position, just keep account of how many times we won the game and how many times we lost it. And that was a sort of basic idea. And just to try and make that a little bit clearer in gory detail, suppose we take a game where we had 9 balls to start with, and Alice took 3 and Bob took 3, and then Alice took 2 and then Bob took 1, and that was the end of the game. Bob lost. So we've got 4 games altogether, and what we want to do is we say, okay, well, the first game was a win, so we increment the count which we're holding for what happened when we had 9 balls and we took 3. And then the next game was a loss, so what we say is, in the situation where we have 6 balls and we take 3 balls, we'll increment the number of times we've lost that game, and we carry on. And so if we have 3 balls, we take 2, we increment the count there. And if we have 1 ball, we increment the number of times we've lost. Now you can see for the last 2 games, things are getting a bit trivial, because if you take 2 balls when you've got 3 remaining, you always win. And if there's only 1 ball there to start with, you always lose. But that's not something which is kind of built into the model. The model just says, I'm going to count these things. And what it looks like in code is very simple. I just have a 3-dimensional array, which is factored along those lines. So the first index is basically how many balls did I start with. The second index is how many balls did I take in that situation. And the third index is basically telling you, am I looking at the wins or the losses? Cheating here actually, because arrays are actually indexed from 0, so it's not really 8 and 3. 9 and 3, it's actually 8 and 2, but that's just to make it easier to read. And the losses are held in the first entry, which is a 0, and the second entry is where the wins are. Okay, so now I've got a number of wins and a number of losses. What do I do with it? I need to extract the strategy from that. And going back to what was on an earlier slide, the idea was that if we win, we make it more likely that we do that thing that resulted in a win, and if we lose, then we're less likely to do that thing when we play the game again. So what we're actually doing is we're building up a probability distribution from the win and loss counts, such that good moves have got a high probability and bad ones have got a low probability. And then all our strategy needs to do is select from that probability distribution to give us the best move. And the good moves will be made with high probability and the bad moves will be made with low probability. And hopefully as we train, the probability of the good moves will successively increase while the bad moves will get much, much less likely. But then the question becomes, how do we generate a probability from knowing the wins and the losses? And this is where things get a little bit more interesting. So you actually look at the sort of raw data that we're working with. This is the output from running the strategy playing against itself 50 times. And in this, if we look here, I've highlighted the line. Well, these are the games where we actually got to the stage where we had 15 balls left, and there are I forget 32 games. No, there's not. That's not quite right. So there's yeah. So there are 15 games which we played where when we had 15 balls, we took 1 ball, and then there's another 5 games where we took 2 balls, and then there's another I can't see because it's hiding behind the video things. There is another set of games which where we took 3 balls and we didn't do very well. So we can see that it looks as if taking 1 ball is a good idea, whereas taking 3 balls is a bad idea. And so what we want to do is we want to end up with a probability distribution which favors taking 1 ball and not taking 3 balls. And it's probably just worth pointing out at this point is that the training has not got very far. And in actual fact, the best move to make in this scenario is not to take 1 ball, but to actually take 2 balls. But it hasn't learned that yet, and it will learn that as we go through more training cycles. So how do we get from counts to probabilities? And I had all sorts of problems with this. The big mistake I made to start with was I didn't actually count wins and losses separately. When I first was building things, I combined them together. So I would say if I've got 10 wins and 5 losses, I'll basically just record the number 5, the difference between. If I've got 10 losses and 5 wins, I record -5. And I could train the model so it would play well as long as you only had 5 balls. But if it had any more, it was having problems. Once I put in the kind of separate counts of wins and losses, then I was still struggling to get traction. And I think that was partly because I've been distracted by my initial mistakes. But I was doing things like putting in logarithms and exponentials and squaring and dividing and other kind of stuff. And although I could get a slight improvement in things, I wasn't really getting very much traction. And I was frankly really getting despairing a little bit. So I put things to one side, did something else, woke up in the morning. I thought, why not just try simple ratios? And that works dead easy. That works wonderfully, and it's dead easy. So what we do is we basically say, take the number of wins and we divide it by the number of losses. And that will give us a relative probability of choosing a particular move. And obviously, the more times you win making that move, or then that probability goes up, and the more times you lose, it goes down. So it has the right kind of behavior. We need to do a little bit of normalization and tweaking, but to take a specific example, if we look back to the data where we had the loss counts where we had 6 balls, then if we took 1 ball in the scenario where we started with 6 balls, we played 20 games and we won 14 of them. If we took 2, we played 6 games and we only won 1. And if we took 3, we'd played 8 games where we did that and we only won 2. So using this idea of the simple ratio, we essentially calculate these relative probabilities. So in effect, it's sort of like about, what is it, 11 times more likely that we are going to take 1 next time compared to taking 2 next time. And it's 7 times more likely that we're going to take 1 next time than 3. And we just need to normalize those. You add up the numbers, you divide through, so you get some normalized probabilities. And once we've done that, things actually seem to work quite nicely. So a little bit more code, and the only reason for showing you this is 2 days work, and I only got 4 lines of code from it. So I felt I'd been a bit stupid, but at the end of the day, it worked. So that was okay. And there's just a little bit of subtlety. We don't want to divide by 0, so we make sure that when we do the calculation, the denominator is always at least 1. But we also don't want any 0 probabilities. And the reason for that is simply that during the training process, because things start off effectively randomly, there will be good moves where you have lost games, but you haven't actually won them. But as soon as you set the probability of any move to 0, the strategy will basically never consider it again. So we never want the probabilities to be exactly 0, although we can have them as small as we like. Looking at the results, because there is an analytic solution, we can work out what the best answer is. Then we can compare the learnt one with the best one. And so the way the results are presented from the training look like this, where we essentially have up here we have the best move from the analytic solution. So when there are 6 balls left, the best move is to take 1. And then we can compare that with a probability distribution. And the probability distribution is ordered in terms of probability. So the one that's first is the one that's got the highest probability, the one that's last has got the lowest. And then we just sort of say whether it's okay or whether it's not. So after 50 games, it's not very proficient. We'll see that you see it says no by 11 balls and 12 balls because it's assigning the highest probability at the moment to a move which is not actually the optimal one to make. And even for situations where it says, well, you have got the right probability there, the probability of you actually making that move is quite low. So for 14 balls, yes, the best move is to take 1 ball, and that's the one with the highest probability, but it's only 39%. It's not very good. But for fewer balls, like about 6 or 7 balls, it's actually getting plausibly plausible. And by the time you've done 500 training runs, it's getting pretty respectable. And if you do 5,000, then you're up to 98% accuracy. And you can see down at the bottom, it takes no time at all to run it. Okay, so any questions?
That's great, Bob. Thanks for that. As I pointed out, you can use the raise hand function in Zoom, and I'll call on you. Or you can put questions over in the Slack channel, the Decision Camp Live sessions. And over there, Jacob has kicked us off with a question. He wants to know if you see a similar approach to be applied in real-world decisioning problems.
Well, I think the idea, I mean, the general idea that's there is in terms of actually getting this adversarial approach where you have the strategy trying to improve things. It is something which I think probably you have to have the right kind of scenario. I mean, for something like, you know, how can I play Go or how can I play chess well, then I think this sort of thing works reasonably well. But if you're looking out into the real world, I think whether you have these kind of adversarial sorts of scenarios is a little bit more debatable. I mean, the more interesting, I mean, you can look at things like gambling type applications, but I think in terms of something like you know, if you wanted to look at it from an economics perspective, then you really don't want to have zero-sum games. What you'd like is to be looking more for scenarios where people are, you know, there's a possibility of mutual profit. But I think the benefit I'd see from this example, if there is any, is really that it kind of demystifies things a little bit, in that you can see, you can take something which is simple and use quite a simple approach, but know that the sorts of ideas that are involved in this, which are things like essentially being able to take data and turn it into probabilities. And the one of the things that you'll see about the way that the system behaves is that if I go back to the previous slide, one of the things that's interesting about this is that early on in the process, one of the things I decided to do was essentially see how many distinct games the system played, because it's quite easy basically to say, essentially assign a tag to every game that you play. And obviously, you know, with a game like this, there are only a finite number of games that you can play. So I thought I'll record how many games I'm actually playing. And if you have, if you play this variation of the game with 17 balls, there are about 18,000 different games that you can play. But I've played this, on this training session, it's played 5,000 games, but it's only played 342 distinct ones. Mm. So it could have played 5,000 completely different games, but it didn't. It's actually constrained them very quickly. And that's because the learning process basically says, don't do this, go somewhere else. So it's interesting in terms of this is kind of showing you not only that it's learning, but as you learn more things, it actually starts affecting effectively the way that you interact with one, you know, the two agents interact with one another.
Okay, so Jacob had, I think, a follow-up question that's sort of related to that. He said that you had said you compared learn strategies with the optimal one, but not during the learning process.
No, I mean, the existence of the optimal strategy is purely on the output. It plays no role whatsoever. I mean, that's one of the other interesting things that you can do is that. I allowed the system to try interacting with a different agent. So although one agent was essentially using the learn strategy, the other agent was either running randomly or running with the best strategy. And I realized that I had actually made a mistake because the two agents are both sharing the same strategy. They don't have they're not independently learning their own strategies. And perhaps I should have done that. But what happens if you get one player using a learning strategy and the other player using a random strategy is it takes an enormous length of time for the learning to actually converge. Whereas if you get it playing against the best strategy, it works very quickly.
Yeah, yeah. Jacob had another little follow-up question about, you know, assuming that one player knew the optimal strategy, would the other player learn it faster?
Well, the way I've actually programmed it's a little bit difficult to tell, but I'm sure that it would do, because it finds, because when the way the learning starts off is basically it works with a flat probability. So basically, it starts off by saying all of the moves have got the same probability, which is, you know, typically 1/3, and it slowly adjusts those until you start sort of picking out the good moves and the bad moves. But if it's playing against somebody who's always giving you or always punishing you for mistakes, you quickly realize that's not the right move to make. So the learning strategy will be much quicker, because you're playing against somebody who already knows the right thing to do. So you get punished much more rapidly than if you're playing against an opponent who's still, you know, trying to find their way as well.
Right. So Denis Gagné had a question about, in the end, who had to do the most learning, the machine or you?
Me. No, it's. I mean, as I kind of said up front. I mean, I did actually sort of. I mean, I kind of sort of said, you know, I threw my hands up in horror, looking at all the possibilities. But I did actually try and see if I could find anything where you have this kind of, you know, try doing machine learning for games. And the problem with a lot of machine learning, when you come up to a sort of problem like this, is that you know, the first things that come up in machine learning are what's your data? Well, I haven't got any because I haven't played any games. And then splitting your data up into training sets, into verification, into validation sets, and into test sets, and none of those sorts of concepts apply in this kind of scenario because it's a different sort of game. So, oh, my video is working now. Oh no, it's gone away again. I don't understand this.
We had you there for like 3 seconds.
Yeah, I know. Anyway, it's. I mean, there are a number of interesting, you know, kind of things to get out of it, I think, but it also kind of brings home that you have to, you know, you have to think about certain sorts of things. I mean, to Jacob's point, you know, I don't need to know the best strategy, in that I can see that the behavior of the system is converging very nicely. So, you know, if I look, for example, you know, I've played 8 balls, taking 3 balls, I've won you know, thousands of games, and lost hardly any. And the only reason why I've lost any at all is because those are, you know, mistakes I made during the training session. Whereas I've almost completely stopped looking at the other options in this. And I mean, I don't really need to know that the best move is 3 because I've got the evidence in terms of how successful it is. But having you know, some kind of checklist like that is useful. But it's the sort of thing that you could do. You can do without, because you can kind of see success in a slightly different way.
Sorry, Jacob, you have your hand raised. Do you want to ask a question?
Yes, you can hear me?
Yep.
I'm just thinking all the time how we can use similar approach in reality. And Bob, I want to suggest scenario what I had to deal with my customer in real life, and to get your opinion. This customer is they create a scheduling software for field service. So they send people all the time to different locations, and they have people have different skills and different service territory and how far they can travel, and sometimes it's not efficient, and they're talking about thousands of people. One of the most difficult things for them was initial configuration of system, learning who can do what and when. But in our case, we try to learn from real things, and one of the feature was not to learn one's optimal strategy. It just does not exist. You're learning from real time events, and you're constantly improving like you did here. What would your comments from this experience to bring it to a similar system like this?
Well, I think if you have a good, yeah, I mean, one of the problems with this is that you only know whether you've done well at the end because you've won the game. But I mean, the generic idea of basically being able to say, I have performed some sort of task, and I have got some sort of outcome from that, and the outcome is good, then that would indicate that the steps I took during that task probably were good steps to take. Now, that's not necessarily the case, but I may have just been lucky. But by reinforcing things, I mean, the point here with things like the win-loss ratio is if I think something's good and it's not good, then what will happen if I persist in doing that is that my bad outcomes will increase, and therefore that will adjust the probability of me taking that strategy, and I will stop preferring it to another strategy which might be superior. So when we saw earlier on that we had 15 balls and the learning strategy was saying, well, the best thing to do is to take one ball, because it persisted in trying to do that, it started losing more games. And so that probability went back down, whereas the probability of the best move, which is actually to take two balls, would be going up, because every time we tried doing that, we would be more likely to be winning. So getting the probabilities to kind of adjust in that sort of way means that you will start preferring good strategies. The nice thing about this game is it's very cheap to run through different sorts of scenarios. I mean, I'm running through 5,000 games, and it's taking me less than a quarter of a second. So that's okay. I mean, if you're doing something over a kind of scheduling period, then you're talking about thousands of things. But again, if you've got thousands of people doing things, if you can manage things carefully, then statistically you can use that as a kind of way of pushing yourself towards the right kind of answer. So I think the generic approach of essentially saying, if I've got a good outcome at the end, then I should start favouring the actions that I took in order to get there, is something which is generally applicable. I mean, the thing is, if you kind of take a step back and think about how do we learn things, we're faced with a number of choices as to how to do something, and we will typically try one or two different things, and we may find one thing which seems to work, so we'll carry on doing that. And if it carries on working, then the next time round we're unlikely to, we're less likely to go to the alternative options, and the more it keeps working, the less likely it is that we look elsewhere. Whereas if we try something and it works a bit and then it stops working, then we're more likely to start exploring other options. So essentially what it's doing is very similar to the way that we learn how to do things, I think, except that unlike us, we can sometimes get fixated on things, whereas this doesn't.
Well, this has been really interesting, Bob. I think we need to close it out. We're at about 30 minutes for the presentation part of this. Jacob, do you want to make any closing remarks before we finish the session?
Yeah, I think it's a very interesting exercise for Bob, and I was very excited reading what he did. And just one conclusion: every time when we deal with machine learning in context of decision management, I feel the most important summary is that we're not creating one optimal strategy, and we put our system in the process of ongoing improvements, and we can learn and we can keep learning. If we can create this environment, that's the most valuable part, instead of trying to reach optimal solution once and forever. So this is probably another lesson what I'm taking from Bob's presentation. And thank you very much, Bob.
It's been a pleasure.
Well, we'll close this out. I will upload the video to YouTube, and I will put the links over on Slack. And thanks to everyone for attending today.
Thank you.
Okay.
Okay. See you next time.